the evidences, diseases are the causes. Okay? In general, computing the probability of the evidence, assessing the probability of the evidence is a pain. So people try not to have to do that, and instead they compute the full distribution for the disease. If they compute the full distribution for the disease, it should add up to 1. That will allow you to get rid of alpha, because the probability of evidence will be the same probability of evidence for every one of these equations. Now for the disease, if the disease is actually a two-valued variable, true or false, the distribution is just two-valued. But it can also be a multi-valued variable, in which case you have to say, probability, suppose you can only have three diseases, A, B, or C. Then you will compute probability of disease A, probability of disease B, probability of disease C, and then they should all add up to 1. Because you have to have one of those diseases. And so computing the distribution allows you not to have to compute the evidence probability. You may think this looks like unnecessary extra work just to avoid computing probability of evidence. But the whole point of probability is assessment is harder than number crunching. Just write it down, if you have a notebook. Probability assessment is much harder than probability number crunching. The whole point of what we have been doing is trying to get by with fewer assessed probabilities. Okay. Any questions? Okay, so next, now what I'm going to do is go through, again, get back to where we were in Bayes networks. Hopefully now you understand a lot more, what we said last class. So we showed a Bayes network like this. So for example, here's a Bayes network, whether cavity to take catch. Okay, catch is this other thing, presumably if you're a dentist, they have that crazy thing that they put in your tooth and it gets caught in the cavity. And you can basically just say, looks like something got caught. And that's a catch. Okay. And so these are the three random variables. And this network says cavity causes both to take and catch. Okay, even though, in fact, all it says is, so I will say the following thing. When I look at a network like this, I tend to say, just like you tend to say, that cavity seems to be causing toothache and catch. But I'll also say in the next 2 slides or so that there is no causality in Bayes networks. You see what I'm saying? You can actually write the arrows any which way, and you will be able to compute the probabilities. If you write the Bayes network in the causal direction, if you happen to know the causality in your domain, and if you write this in the causal direction, you typically tend to have fewer dependencies. But that is only the case when you have an expert who understands how the domain works. If there is no expert, then you don't know what causes what. Okay? So in fact, to bend your mind a bit on that, there is this saying that has anybody checked whether laboratory rats are predisposed to getting cancer? Why is that funny? If at all it's funny. Because most of the studies on cancer would involve essentially pouring various things, chemicals into these laboratory mice and seeing if they get cancer. And every day there's yet another thing saying coffee seems to cause cancer, ice cream seems to cause cancer, broccoli seems to cause cancer, everything seems to cause cancer. So at some point of time you might say, maybe the real problem is the mice get cancer for no good reason. The reason I'm saying this is you don't actually know the causality of cancer. If you think you know the causality of cancer, let me know. And there are like $1 million prizes for that. Okay? So when you know the causality, it's easy what the causes are. But most of human civilization is not knowing what causes what and figuring that out extremely slowly. Remember that all our ancestors were pretty dumb people. For the longest time, they thought the sun is going around the earth. You can laugh at them. But that's what they thought. And in fact, the non-causal models tend to be extremely complex. I may have mentioned this at some point of time. So if you see the way the complexity of the planetary models kept increasing, When people said, obviously you can see sun is going around the earth because the sun seems to come like this and go down like this. And like this, there must be sun is going down, going around the earth. Then you come up with some point to them, saying, no, look, notice you can't explain this. Then they'll make the modeling more complex. Then you say, here is this other problem. They make the modeling more complex. So there is a museum that I saw in Madrid, which has this whole bunch of these actual planetary models. Okay, Earth-centric planetary models. Each one way more complex than the previous one. They were making it more and more and more and more complex to handle all the edge cases. And then Copernicus said, Bozo, stop doing this, put the sun in the middle, you'll have a much smaller one. You see what I'm saying? It's easy to laugh. It's hard to figure out causality. Okay. So anyway, that's your cavity catch thingy. So and then I showed you this particular example with Pearl example, on the Bernoulli earthquake thing. And I told you, and in fact you have used it many times, I told you that the way the joint distribution in Bayes networks, and you can get joint distribution entries from Bayes network, is essentially by using this independence assumption, that a node is independent of its non-descendants given its immediate parents. So it's independent of its siblings as well as its ancestors given its parents. Which allows you in 2 steps to go from, if I want to compute this, J and M and A and not B and not E, I can first use just direct chain rule. In using this, I didn't do any magic. And then, having done that, then I say, now I look at the network and say, J given M, A, E, B is nothing but J given A. Because John is somehow inoculated. John is inoculated from everybody else. I mean, from his sibling nodes and the ancestor nodes. Not its descendants. In this network, it doesn't have any descendants. It will be inoculated from its siblings and its ancestors given the parent. That's the independence relation. That's really the only thing that you need to use, and then you'll get the joint distribution. Right? And we argued that if you know the joint distribution, you can answer any possible probabilistic way. Right? Okay. That's basically this thing. So it turns out that the real semantics for Bayes networks is this notion of independence assertions. What is independent of what given what? Okay? So really, a Bayes network can be seen as capturing a set of conditional independence relations. It's a very abstract thing. You wish it was something much less abstract, but really that's what it is. The Bayes network really only captures conditional independence relations. It captures like the set of variables x is independent of the set of variables y given the set of evidence variables z. That is a conditional independence assertion. Now the reason conditional independence assertions are good is because they allow you to factorize probabilities. If you have a complex joint probability, you can write it as simpler multiplication of simpler, smaller probabilities. That's why you like independence assertions. So the kind of independence that you knew was unconditional independence. A is independent of B, like completely. In which case P of A and B is P of A times P of B. This everybody knows. But the more interesting one is A is independent of B given C. Okay? And if that is the case, then what you can do is, for example, if I have this true, then I can simplify lots of things. For example, in that case, probability of x and y given z can be written as probability of x given z and probability of y given z. And similarly, probability of x given by z can be written just as probability of x given z. And similarly, probability of y given xz can be just written as probability of y given z. With just that one independence assertion, you can do all these simplifications. Okay? In particular, if I just have, so here notice x, y, and z are sets of variables. Most generally speaking. The simplest case would be each of them are single variables. They are singleton sets. Okay? And so if A is independent of B given C, A is independent of B given C, in essence, normally you can write that in a Bayes network by putting C and putting A, putting B like this. In this case, A would be independent of B given C. You can also do this. C, A, B. In that case too, A is independent of B given C. In both those cases, that independence relation holds, and when that holds, a whole bunch of simplifications can be done. Okay? So, and of course, when there are simplifications like this, then the independences reduce the number of numbers you need. That's what we found. Essentially, the number of numbers that we need. So, an idea then is, why don't we just write down, for a given probability distribution, why don't we just write down all the conditional independence assertions that just hold here? Why, muddle around with these networks? And it turns out, given any arbitrary probability distribution involving, let's say, n variables, there can be exponentially many such assertions you can write. You understand? This is embarrassment of riches. You wanted independence assertions, I can give you a whole bunch of them. They're all independence assertions. Writing those exponentially many independence assertions becomes highly non-compact. So you can think of a Bayes network as a very compact way of writing down, in essence, all the independence assertions that hold in your distribution. Okay, before I go forward, I want to ask you the following question. Suppose I want to check suppose I want to check if it is indeed the case A and B are independent of each other given C. If I want to check if this is true, really speaking, not because the network is saying, but is it true in the real world for my A, B, and C? Is there an experiment I can set up to check that? Yes, essentially, you will set up a frequentist experiment, right? You will consider essentially whole bunch of words, okay, let's say 1,000,000 words, and see the fraction of them where C is true. Let's say 1,000 words of these 1,000,000 words C is true. Then see the fraction of these 1,000 words where A and B are true. Let's say that's 5. Then probability of A and B given C, so A and B together are true in 5 words. Actually, yeah, 5 words, okay? So then the probability of A and B given C would be 5 by 1,000. Right? Now I'll do the same way, probability of A given C and probability of B given C. And see if the multiplication of those two numbers is equal to 5 by 1,000. If so, then the independence holds. So there is actually a way in which you can check whether independences hold. It's not just a completely abstract concept. Yes?
Can you check independence using OR, A or B, and then use an addition between P and
No, but the most interesting, yes, you could get into that direction, but really my important point is most of what we are doing is these conditional independences are A and B are independent events. Okay? So understand that independence actually has ground truth. You can actually evaluate it in the real world. What the network is telling you is you don't have to go out and check everything. This is the model of the world. So you can take it from me. I did all the hard work. So if you were to actually test it, it will hold in the real world. Okay? So conditional independence assertions, you cannot write them all because there are exponentially many conditional independence assertions that hold in a domain. So the brilliant idea is just we want to implicitly specify the conditional independence assertions. That's what graphical models do. Did I say the word graphical models before until now? If not, now I said it. Okay, that's the other thing that people use. Graphical models or graphical probabilistic models are either Bayes networks or Markov networks. So you are essentially, the graph is telling you what independence assertions are. Okay? And if the independences hold, and there are two things that everybody should understand about independence assertions that hold, and then I'll also show you at the end of today's class, and right after that, actually checking whether any arbitrary independence relation holds in a given network. And that's the whole baseball algorithm that I'll show you in a minute. Okay? But these are two things that you need to understand. One, of course, is this. This independence holds in any Bayes network, which is a node is independent of its siblings. Okay, so X here is independent of all its non-descendants. So these are its descendants, so it's not independent of them. It's independent of all its non-descendants given its immediate parents. So these are its immediate parents, and they somehow throw in a half-closed blanket around it. A half-closed blanket. And say, we'll protect you from the ancestors and your siblings. But you deal with your own children and your grandchildren. Okay? That's what we've been using till now. There is a generalization that will also hold, actually. And in fact, they follow from each other. And that is Markov blanket. And do you know what that is? Okay. Linus with his security blanket. Okay? So you have your security blanket, your Markov blanket, and if you know all the people in your Markov blanket, you know where they are, then the rest of the world can't affect you. The only way the rest of the world can affect you is through your blanket. Okay? And so Markov blanket essentially generalizes this idea by saying a node's Markov blanket involves its immediate parents, its immediate children, and its children's other parents. Sort of nuclear family. If I know what the values of my children, my parents, and my parents' step-parents, that's my security blanket. That's the family values as far as Bayes networks are concerned. It's extremely useful. Everything else, this network, outside of this blanket, this network can be million nodes. And the influence of those million nodes on X, the probabilistic influence of those million nodes on X is the same as probability is the influence on X by just its Markov blanket. In fact, just to kind of get you interested, although I won't give the technical details right now, some of you may have heard of something called MCMC. Another of those things that increases your chances of getting a Google interview. If you throw in MCMC. Markov chain Monte Carlo. But we will get up to it, maybe next class. It's basically a sampling approach for improving inference on networks. And Markov chain Monte Carlo essentially samples a node given its Markov blanket. The Markov blanket isn't just an idea that I'm doing to keep you here until 11:20. It's a very useful. So this you use anyway, just to understand Bayes networks you are using. This you use when you do Markov blankets. Okay, but here's the one thing about semantics. Hackers don't need to know what the semantics are. If you just want to hack Bayes networks, you don't care about semantics. It's not like you would need that every day. However, the way you prove the correctness of your algorithms is using the semantics. In that vein, I will end with this. This is probably like the next 10 minutes will be just going through this. This is, those two are two special cases of independences that hold. Okay, in particular, I just said, in this case, I said X is independent of Z's given U's. And similarly, I said X is independent of the world given U's, Z's, and Y's. Those are the independence relations that I wrote there. But what I want to know is, I just come up with an arbitrary independence relation. And I want you to tell me, does it hold or not? Okay? So let me just do this. So here's my network. I want to ask the following independence relations. Do they hold or not? What do you think? How do I tell? Do you understand what I'm just saying? So let's actually try to see. In this network, given this network, do we believe, given the network semantics, is B, that is Burberry, independent of Mary calling given alarm? What do you think? Let me actually start slightly. Okay. Is Burberry independent of earthquake by itself, given nothing?
Yes.
Is Burberry independent of earthquake given alarm?
Yes.
Is Burberry independent of earthquake given alarm? How many of you say yes? How many of you said no? Somebody who said no, tell me why. So think of the, basically think of the plausible reasoning, okay? Yes, please go ahead.
There's the children's other parents.
I understand, but you're telling me the definition. That's not the way. So the question is, do you think, is Burberry independent of earthquake given alarm? Yes.
Because if there's an alarm going on, if there's not an earthquake, then there's probably a burglary.
No, the opposite way. If you already know burglary is occurring, and alarm is going off, your need to believe that there is an earthquake reduces. Did you understand what I just said? Two causes causing alarm, if one of those causes holds, the other cause is not necessary anymore. You see what I'm saying? Okay, it's not necessary. So in fact, this you would like to say doesn't hold, because burglary explains away earthquake when there is an alarm. I'm sorry, alarm is explained by burglary, so you don't need earthquake. So this is called explaining away. And you do this in real life. You see what I'm saying? You see somebody who's dead and they have like a huge big hole, bullet hole on their head. You don't then check, maybe they also have Ebola virus. And it just so happened that they had Ebola as well as bullet hole. Plus somebody basically came and hit them from behind, all these things. You don't check for that. Because you have a good explanation, that's good enough. That's explaining away. So when this happens, in fact, I want to be able to say that this does not hold. B is not independent of E given A. How about B independent? Is B independent of E given Mary calls? For about the same recursive reasons, it won't be independent, because Mary calling sort of is kind of causal direction. Alarm happened, so Mary called. And alarm happening can be explained by any one of them, so the other one is not needed. This is the explaining away reason. And the other ones you pretty much understand. Is B independent of M? Is burglary independent of Mary calls given alarm? You can kind of see that probably is the case, because in essence this network is saying the only reason Mary calls is because of alarm going off. So if burglary has to affect Mary calling, it has to affect it through alarm. If you remove alarm, Mary calling is independent of burglary. So in doing this, in checking this, actually, you can think of independence as removing nodes from a graph and see if the two edges and two other vertices will become disconnected. So I would say burglary is independent of Mary given alarm, because if I remove alarm from consideration, if I remove it from the network, there is no way of going from burglary to Mary calling using the edges. You see what I'm saying? So that's why, in fact, basically Mary calling is independent of burglary given alarm. Okay? Similarly, John calling, Mary calling, independent of earthquake. John calling, Mary calling, independent of earthquake given alarm. Again the same. Because if I remove alarm, there is no way of going from earthquake to any of these two ways. Agree? And then finally, is B independent of E? Well, clearly there is like no path directly between B and E, given nothing. So it turns out that the intuitions are telling us that this stuff is independent because paths are blocked by evidence. Given X means X is evidence. On the other hand, this stuff is not independent because path is blocked. You see the crazy nonsense that's going on here. Okay? I mean, so somehow we don't like alarm being present. If alarm is present, then burglary will become dependent on earthquake. But if alarm is present, burglary becomes independent of Mary calls. What you would really like to do is have a simple explanation that holds independence assertions. Will basically say the independence assertions hold if you remove the evidence nodes, X and Y, so you are saying X is independent of Y given Z. Okay, so if I remove Z from the network, then X and Y will become disconnected. If I could do that, life would be really simple. Unfortunately, you can't do that in Bayes networks. If you want to do that, go to Markov networks. That's the difference between Bayes networks and Markov networks. In Markov networks, they have essentially undirected edges, and independence is just simple graph disconnection. But in Bayes networks, actually you have to deal with this subtlety that certain paths, what are called causal paths, will be blocked. But for other paths where the same evidence is caused by two possible things, they will become dependent if you give the evidence. So now I go back to my previous slide, and everything is shown there. So there is a huge big network. Okay, I have some set of nodes X here, some other set of nodes Y here, some intermediate set of nodes Z which are given as the evidence. This is all abstract right now. Some intermediate set of nodes Z given as evidence. Okay? And these other nodes essentially are not evidence. Unless you have it in the gray, it's not evidence. So then you can talk about paths. From X to Y, you can think of paths. So a path like this, first, let's see this one. The first path, the green path, notice that the X, from X to Y, when it comes to Z, an arrow is coming in, an arrow is going out. You can think of this as a causal path. That means X is causing Z, which is then causing the downstream. That's the causal path. A path can be a causal path. A path also can be common cause path. I'm sorry, this is a causal path, this is a causal chain path. There is a common cause path where Z, at this point, when the path from these nodes to these nodes, when it touches an evidence node, at the evidence node, the arrows are going out of the evidence node in both directions. that would be called the common cause path. So Z is causing both X and Z in essence. I mean, Z is causing both X and Y in essence. So that is like, if C causes A and B, if you give C, A is independent of B. If B is causing C, C is causing A. If you give C, B and Z is independent of A. Those two are essentially, causal chain can be blocked by given evidence, and common cause also can be blocked by giving evidence. There is one other thing, where the two arrows at the evidence node are coming in, not going out but coming in. That means Z is a common effect of both X and Y. That's what happens in alarm given burglary and earthquake. Both earthquake and burglary are causing alarm. Such a path is blocked only if Z is not present in the evidence. If it is present in the evidence, the path is not blocked. You get this? Okay? If it is present in the evidence, it's not blocked. If it is not present, then it is blocked. That's the rule. That's the rule there. You use that rule, you will be able to answer, in essence, all of these questions. Particularly, we will see that these will all hold, because go from B to M, the only path between B to M is this path. It's going into alarm, coming out of alarm. So it's a causal chain path. So if alarm is known, then this path is blocked. If the path is blocked, then burglary and Mary are independent. Similarly, so that means this is correct. And John and Mary given earthquake, and John and Mary independent of earthquake given alarm, it's the same reason. Earthquake is causing alarm, which is causing John cause. And earthquake is causing alarm, which causes Mary cause. When I say cause, it's just the arrow direction. And both of them would be blocked if alarm is given. And the alarm is given. On the other hand, burglary is not independent of earthquake given alarm, because this is a common effect. Alarm is a common effect. And if you give the alarm, then the path is not blocked. If you don't give it, it's blocked.
Can you explain the second one?
Which one? Just a
John
minute.
and Mary.
Yeah, so John and Mary cause can be written basically as John is independent of earthquake, Mary is also independent of earthquake given alarm. And so you can take John and earthquake. The path between John and earthquake is the only path. And you are going through it as a causal chain. Very simple. And causal chains are blocked. Okay? And in fact, John is, you can also say, one of the other things that I did not write is John calling is independent of Mary calling given alarm. That also is true. Because the only way John calling and Mary calling are connected